Physical computing students. So for week 4, our students had a very brief in-class quiz. There were a couple of multiple choice questions plus one build, and this was the build question. So at Boston College, our academic rival is a certain institution in Indiana that has a French name, but calls themselves the Fighting Irish. Sounds a little confused to me, but in this problem we assume that real leprechauns come to Boston College and ask you to use your yontach, meaning fantastic in the Irish language, CircuitPython skills to code a CPB that sparkles in green when the leprechaun dances. Now, we'll assume a dance is detected when a shake is detected. There's a folder with 2 sounds at this URL. The folder is called Irish Sounds. The 2 sounds are named sound0.wave and sound1.wave, and when a shake is detected, you should play a sound alternating the sounds with each shake, 0, 1, 0, 1, and while the sound plays, you should sparkle the CPB lights at random in green, holding on each light for 1/10 of a second before turning it off and restarting. So this one challenge has you working with neopixels, randomization, sounds, performing a function in parallel with sound play, working with the accelerometer, and working with conditionals and arithmetic logic so that you can alternate sounds. As always, I show my students what the solution should look like, and here it is.
Gannach dína féile pórigar. Gannach dína féile pórigar.
Now before showing you the solution, let's talk accelerometers and acceleration. Now, students stayed after class to ask me about the 3 types of acceleration, and although you've had learning videos on all of these, I thought that it would be worth explaining them again. So we have 3 different types of acceleration that we can detect. One is the triple axis movement, meaning which way are we tilting the CPB, and the other is for detecting taps, and the other is for detecting shakes. Now, the problem asked you to work with shakes. That's how you detected the leprechaun jumps, but first let's look at the triple axis tilt. So I'm going to highlight this code here, which is the code to set up the accelerometer for the CPB, and this code just below it for detecting, printing, and plotting the readings for the 3 axes, X, Y, and Z. So I'm going to copy this, go to Moo, and paste it into a new document. Shift-Command+ will increase my font size, so will clicking on the zoom button. And by the way, the accelerometer on the CPB uses a chip called LIS3DH, not a friendly name, but that's why we're importing LIS3DH. And accelerometers with this chip are also available as external sensors if you're ever working with a board that doesn't have a built-in accelerometer. Most boards don't. Now, I want to detect the accelerometer movement over and over again, so I'm going to do that inside of a while true loop. I'll add that here before the accelerometer reads in the 3 values X, Y, and Z. Remember, while true has a capital T true and it has a colon at the end, and we need to indent everything that will be inside the infinite loop. So I'm going to highlight these 3 lines here and press tab, and they're indented. And I'm also going to add a time.sleep passing in 0.1 just to make sure that I slow down the reading of the acceleration so that my print statements aren't left behind, because the while true loop will execute much faster than it prints on screen. Now I've also got to remember to import time. I'll click on the save button and I'll save this file to my CircuitPy volume, making sure that I save over any existing code.py there. And it starts running. So we have 3 axes. X is left and right, Y is up and down, and Z is if you flip it over. And if I lift up my CPB, you can watch what happens in the plotter and also what's printing out here. If I tilt forward, we see that the Y-axis starts to go forward until it's a little over 9, which is 1G in the one direction. Then if I tilt it at a 90-degree angle in the other direction, I get about a -9. Then if I tilt it to the right, the x-axis starts to move to a maximum of about 9. And then if I turn it to the left, I get a -9. And then if I flip this entirely over, you can see how that changes from about 9 till a +9. So again, about 9.8 is the gravitational acceleration at sea level. If you ever hear people talk about G-force or pilots or astronauts talking about how many Gs, that's how many times the Earth's gravitational pull the particular force is, which is about 9.8 meters per second squared. Whenever I use the accelerometer, I always print out and then also print the tuple inside of an extra set of parentheses so that I can plot things out and remind myself how things are going to change if I tilt tilt the accelerometer in different directions. Also, be sure to add a time sleep in there, otherwise your print won't catch up to the actual accelerometer readings. Also note that if you're going to shake your accelerometer, you're going to get a gravitational force that's greater or less than the gravitational force of the Earth. So that's why you either get above 9.8 or you get below negative 9.8. So now let's explore taps. So I'm going to delete the X, Y, and Z axis code. And when working with taps, we have an additional step we call the set taps method. Only when you deal with taps do you want to include this, otherwise don't include it. Now this set tap methods here, which is on the accelerometer that we set up above, has two parameters. The first parameter is how many taps we're detecting. 1 detects single taps, 2 detects double taps, 0 disables tap detection. Now this isn't super accurate, so it is possible, depending on what the range settings are and the sensitivity settings, that you might detect multiple taps when you have single tap selected, or you might be detecting more or fewer double taps than you'd intended. So if you're not getting the results that you want, then you can play around with your threshold value and your range value. That brings us to the second value, which is the threshold value. The higher the value in here, the less sensitive your tap detection is going to be. Now threshold is just a little bit more complicated because it works within a range setting. So here I've selected 20. Now that matches up with the upper or least sensitive range for the 8G setting. These range settings here refer to the G value that you set up when you set up the accelerometer. I've chosen the upper value for the 8G range here because if we scroll up, we can see that I've set my range value in my setup code here for 8G. That means that I've got a range of 8 times the Earth's gravitational force, which is quite a bit. Not sure if I'll ever shake or tap in that range. Smaller values for a range have a finer grain sensitivity. 2G is more sensitive. If you're detecting really heavy taps and you don't want your tap detection to be that sensitive, you can increase the G range. The sensitivity that you set for your G range is going to apply to all of the other kinds of accelerometer readings as well, so it'll apply to what you can read in X, Y, or Z, or the sensitivity of the shake. So I can start by setting a 2G if I want to be sensitive, or 8G, 16G if I want to be less sensitive. Then I can modify my threshold parameter to tweak the sensitivity within that range. When working with taps, just make sure that you set a threshold, which is within the settings for the G range setting that you set. So back in Mu, we can see that I get an 8 range here. Let's keep this for our test of taps, and I'm going to copy the set_tap method, which again, you'll need for taps, but only for detecting taps. This is detecting a double tap at the harder to detect or less sensitive range for 8G, and I'll also grab this if statement here, which will be true if the tap is detected. Then I'll return to Mu, and I'll paste this above the while true, although actually, I want the if statement inside the while true. That'll allow me to check the taps over and over again in my infinite loop, and I'll be sure to indent these, otherwise I'd get an error because everything under the while true loop that's going to execute needs to be indented. I'll add a comment above accelerometer set taps, which says set up taps. In under the if accelerometer.tapped statement, remember that's going to be true if it's tapped, so I'll just print out in between parens and double quotes, yow, you tapped me, open curlies, num_of_taps, close curlies times, make sure you close quote and close parens. And actually, this is a double tap I'm detecting, so I'll put in a you double tapped me. But we haven't created this num of taps value. So this is a variable we could have named any name we want, but we're going to use this to count the number of taps, or count the number of double taps, I should say. We'll count them one at a time. Each double tap is 1. So up here, I'm going to set num of taps equals 0 before the while true, so we start counting at 0. Then if a tap is detected, I'm going to add 1 to the num of taps by saying num of taps plus equals 1. And I almost forgot, this print is an F string, so I need to put a lowercase f before the double quotes because I've got curly braces and a variable inside. Then after the print statement, I'll say time.sleep, and in parentheses 0.1. This will make sure that I don't detect taps any faster than 1/10 of a second. With taps, there's sometimes a risk that if you tap the table really hard, there might be a bounce back on the table and you might detect more taps than you mean to. By saying sleep for 1/10 of a second before trying to detect the next tap, hopefully that will prevent the bounce back from registering twice. So again, the tap detection isn't perfect, but I'll save and open the serial console and let's try it out. So if you experiment, you might find sometimes you are detecting taps, sometimes you're detecting double taps when you only tapped once. Again, it's not perfect, but you can tweak your range values and your threshold if you want to. For my range and threshold here, it looks like sometimes hard single taps are being detected as double taps. And if I look back at my documentation, I can see if I want to be more sensitive, I could set this to 2G, but the upper end, which is the less sensitive amount of 2G, would be 80. So I'm going to set my accelerometer range to 2G instead of 8G, and I'll set the tap threshold to 80. Let's try this out. So I'm not sure if you can tell, but I'm tapping much lighter here, and it's detecting most of those taps, not all of them. And to try out a range that would make it harder to detect double taps, why don't we set the threshold to 10 and the accelerometer range to 16. And again, on the tip sheet, we see a threshold of 10 at 16G is the least sensitive for the widest range of G forces. So now let's save and open the console and take a look. If you watch this, you'll see the first few light taps weren't detected. At 16G, I've got to tap much harder than I did at 2G for them to be detected. Even again, it's not perfect. It might also be that my time is a little bit too high for my detection here. I'm not sure. So now let's delete the tap code and work on shakes. So I'm going to highlight the set tap. Again, you only need that for taps. I'll delete that. Then let's count the number of shakes instead of the number of taps. So I'll change the name of this variable. I'll change my F string so it reads, yow, you shook me, num of shakes times. Let's make sure we're incrementing num of shakes now, not num of taps. And I'm going to highlight and delete this if statement here because this is detecting taps, and now we want to detect shakes. And this is the shake code. It's a simple one-liner. We say accelerometer.shake with a shake threshold in there. Shake threshold is how sensitive it should be in detecting the shakes. The default is 30, so if you don't put any value in here, it's going to be 30. Again, larger values are less sensitive. 10 is most sensitive, so I've got a 15 in here. I'm right about in the middle. We don't have to calibrate any sort of threshold ranges with shakes like we did with taps, so I'm just going to return to moo and paste this in. I'll indent the line in the two comments below while true, and this accelerometer.shake is going to return true if there is a shake. So I'm going to turn this into an if statement with if accelerometer.shake with a shake threshold in here. Make sure you always put a colon after your if statement or it won't run. My comment says true if shook. Actually, it says of shook. It should have said true if shook. And again, if you wanted to, you could completely delete the shake threshold in here, and that would put in 30 by default. But why don't we keep the shake threshold equals 15 in here? Then let's save this and take a look at the shakes. Now this seems to be very sensitive, so what I'm going to do is I'm going to put a quarter of a second in here, so I'll only detect a shake every quarter of a second. Now this still isn't great detection, but we're going to see we get really distinct shakes when we do our quiz build, because after we detect a shake, we're going to take the amount of time that it takes to play each sound. That's much longer than a quarter of a second. So let's work on our solution, and you'll see that I build the solution testing each part one at a time. It's usually better to do that to make sure that you have each section working instead of trying to do it all at once. If you try to code all the parts without testing each individual part, then you might not be sure where your error is, or it'll be harder to find errors. So I'm going to need to flash my neopixel, so I'm going to set up pixels equals neopixel.neopixel, and in parentheses board.neopixel, comma 10, very familiar to us. Then I'll create two colors, green, which equals in parentheses the tuple 02550, and black, which equals the tuple 000. Now we're also going to want to play audio, so let's head over to our tip sheet and take a look where the CPB audio play stuff is. I'll grab and highlight this code to set up the CPB speaker. I'll copy it and paste it into moo. Right underneath the other import statements is a good place for this. I'm also going to use my play sound function, so I'm going to grab that, copy it, and I'll paste that into my code. Now remember, this path here is the name of the folder that holds our sounds, but we've downloaded the iris sounds at the URL that I gave you in the question, so we want to make sure that we change the name sounds to iris sounds, spelled exactly as it is in this folder. So I'll copy this and paste this over sounds. And watch this, I'm about to make an error, so I'm copying my Irish Sounds folder into my 2 terabyte drive. I missed my CircuitPy drive, so my code will give an error when it runs, but I'm going to leave it in there so that we can see what kind of error we get if our code can't find the file that it needs. Now we're not going to count the number of shakes, so I can just delete this variable, but I do want to alternate between the sounds. And if we take a look in that Irish Sounds folder, just as it said in the quiz question, the two sounds are sound0.wave and sound1.wave, spelled in all lowercase. So I just want to alternate between sound 0 and sound 1. I want to change that sound number, so I'm going to create a variable called sound_number and set it equal to 0. Then I'm going to highlight and delete all this old code that was inside the if statement that detected if the accelerometer was shaken. And instead, if I detect a shake, I'm going to play _sound. That calls the play sound function. I'm going to pass in an expression that's going to calculate the name of the file. So it's either going to be sound0.wave or sound1.wave. And for the number in that name, I'm going to use the number sound number. So I'll enter the string sound, which is the first part of the name. Then I want to add in sound_number, but that's an integer. It's a number. It's not a string. So to add a string with a string, what I need to do is I need to type convert. So I'm going to say plus str and then in parentheses sound underscore number. Then to that, I'm going to add the string .wav, which is the ending or the extension of the sound file. So this will print out a string named sound0.wave or sound1.wave if I increment sound number. Now before I play this sound, I want to turn all the pixels green. I'll eventually want to sparkle them. But for now, just above play sound and indented at the same level, I'll say pixels.fill and pass in my color green, all caps. And then after I play the sound, I'm going to say pixels.fill, passing in between the parentheses black. And let's save this and go up to the serial monitor and see how this looks. And I have an error in here. I can't see it with the default type size and moo, so I'm going to grab and pull up my serial monitor to give myself some more room, and aha! I see I've got an error in line 44. It says invalid syntax. There's nothing wrong with line 44, but as mentioned, sometimes the error is in the line above, and sure enough, I forgot my closing parenthesis for my play sound function call. I'll add that now and save again, and another error in line 1. Sloppy professor, the module is not named pixels. It says no such module pixels. Of course, the module is called neopixel singular. Now I'll save. I don't see any errors, but watch what happens when I shake my CPB. Another error in line 43 of my code, which then calls 19 of my code, and I get an error, no such file directory irisound/sound0.wave. Now, not only does it say it's in line 19 of code.py, but it's in the play sound function. Do note, sometimes you get some errors down here that have additional lines after your code.py file. That might occur if you passed a bad value into a module, so you want to take a look at the last line that's mentioned in your code.py file. That's probably where you'll find your error. Remember, I pointed out that I actually missed when dragging my irisounds folder over. If I look at my CPB, I can see I don't have a directory in there named irisounds with a file called sound0.wave inside of it. So if you ever see no such file or directory, you're trying to access something that doesn't exist on your CPB. Let's fix this now. I'm going to drag over my irisounds from my desktop into my CircuitPy volume. And I don't even have to save or rerun my code. My code runs automatically. I didn't make any changes to my code here. Your board will automatically re-execute when the files on the board change, so I can pick up my CPB and shake it and give it a try. And all right, with each shake, we turn the pixels green, we play a single sound, sound 0, then we turn the pixels black, and we keep looping over and over again inside of while true until we detect another shake. So now let's alternate between sound 0 and sound 1. There are a few ways to do this. What I'm going to do is right underneath where I play my sound, I'm going to take the variable sound underscore number and plus equals 1, which means add 1 to that value. So if sound number was 0, then sound number is ready to be sound 1 the next time it's played. But if it was sound 1, I just increased it to sound 2, and there is no sound 2. But underneath this, I can say if sound underscore number greater than 1, colon, and indented below the if statement, I can say sound underscore number equals 0. There are a bunch of other ways to do this, but hopefully this way is clear. Let's save this and give it a try again. And I didn't do this, but note that you always want to have your serial monitor open when you save code that you've changed, because if you got any error, it would show up in your serial monitor. Sometimes students are confused what's going on in their code, and they haven't looked in their serial monitor to see an error. So we shake this once, sound 0 plays, but also what happens is sound number is being incremented. So the next time we shake it, sound 1 plays, then what we do is we increment sound number 1 again, but since that's greater than 1, we go back to sound 0 and sound 1 continue to alternate. Nice! So finally, we'll add a little sparkle to our board, and we want to do that inside of a function so that we can call the function instead of calling pass when we're playing our sound in our play sound function. So I'm going to define a new function above my while true loop with def space. I'm going to call this sparkle. We always have an open and close parens for our function. If we were passing in any values, we'd name them inside of the parens, but we're passing in no values. Always end the function definition line with a colon. A good rule of thumb is if you have to indent underneath it, you need a colon above it. We press return, we're indented, and since I want to sparkle a random value for the number of LEDs, I could put that in as the literal number 10, but instead above pixels, I'm going to create a constant value called LEDs in pixels, set that equal to 10. I'm going to replace my 10 with LEDs in pixels. Then down here, let's find a random LED. We'll call this random underscore LED. We'll set it equal to random.randint, and in between parentheses 0, comma, LEDs in pixels -1. By saying -1, we're going to come up with a random value between 0 and 9. Remember, we're 0 index, so we don't have a value named 10. Then we'll say pixels in brackets random underscore LED. So that's going to light up the pixel at that particular LED number. And we just set this equal to a color. We'll set it equal to green. Then I said that we should sleep for 1/10 of a second after we flash the color. So we'll say time.sleep and in parentheses pass in 0.1. Then we want to turn off the light that we just shined. We'll actually turn off all the lights. That's easy. Pixels.fill and in parentheses black. So this is going to flash a random LED in the color green for 1/10 of a second. It'll do that over and over again as long as sparkle is called. So I no longer want a pixels fill green before I call play sound. I'll delete that. I also don't need to call black to turn the pixels off because I do that in my sparkle function. But, and here's that important bit, I want to make sure that I call that function while my sound is playing. So up here in my play sound function, where it says while audio.playing, I'm going to replace pass, which does nothing while sound is playing, and instead put in a call to my sparkle function, which is just sparkle, open and close parens. No colon after calling the function, only when you define the function. I've seen students make that error as well. So this runs the sparkle function while sound plays. Let's save. Open up our serial console so Moo doesn't catch any errors and I can run my code. When I shake, oh, I've got an error and I'm thrown into the REPL. And look at the error in here. It says name error random is not defined. Oh yeah, I forgot to import random. I'll fix that up top. Although look in the console, I've also fallen in the REPL. I can see the 3 greater than symbols there. You also know that you're in the REPL because all the lights in your CPB will light up as white. So if I press Control D, I'll get out of the REPL. Remember, I've got a red dot next to code.py indicating that I haven't saved my code. So I got to click on the save button. My code runs. I don't see any errors in the console. Nice. Let's give this a try. Give that a shake. And oh, look at all that sparkly leprechaun goodness. And when we shake again, we can see that we're alternating sounds. We can see when the sound is done playing, all the lights in the CPB go off. Excellent work, Pythonista. Hopefully your quiz challenge went well for you. If not, hopefully you understand now how to solve problems like this, and you will in the future. If you didn't get full credit, then you do have to resubmit a fully correct solution for next week's homework. No need to do that if you got a perfect on the quiz, and no need to submit any corrections if you got any of the multiple choice wrong, but do make sure you know the correct answers. I hope that you also paid attention to all the tips and the tricks shown in this lesson. We won't have a full solution video like this each week, but I wanted to make sure this week that we covered lots of basics that I've seen trip up students in the past, so now you are armed for rest of semester goodness. Now take those skills and make something awesome.